Hi, I'm Kurt Clothier with Figure Engineering. We've identified that the United States Air Force has experienced compliance citations for personnel exposed to hazardous levels of hexavalent chromium and cadmium. To solve this problem, we've developed the Advanced Continuous Time Adaptive Ventilation System, or ACTAV for short. ACTAV is a collection of sensors, controllers, and actuators used to monitor and control a blasting environment with the goal of reducing operator exposure to hazardous airborne toxins and to meet changing safety standards while maintaining reasonable operating costs. Occupational exposure to hexavalent chromium is 8 times more likely to cause cancer than asbestos. Workers are exposed to airborne chromium when they inhale dust from aged coatings that are stripped by abrasive blasting in a blast cleaning room, often referred to as a BCR. These BCRs typically have poor ventilation and also leakage that affects personnel in the surrounding area. There are 2 major problems with current blast cleaning room technology that puts all workers in a blasting environment at risk. The first problem is that blast cleaning rooms have poor ventilation due to either insufficient airflow or poor scavenging of that flow to adequately remove airborne toxins from the BCR. This leads to operator exposure above the OSHA time-weighted PELs. Simply increasing the airflow to reduce exposure is an expensive proposition. Energy costs increase exponentially when a fixed parameter airflow is used to mitigate airborne toxin exposure. Therefore, there's an urgent need to manage exposure at a reasonable cost. The second problem is that dust migrates outside of the BCR, either by leakage or drag out, putting all workers in the vicinity of the abrasive blasting environment at risk for cadmium and chromium exposure. The ACTAV system solves these problems by using multiple sensors to monitor the blasting environment and adjusting the airflow accordingly. The system controls the airflow with a series of VFDs and mechanical effectors that vary the air supply to the blast cleaning room. The result is ventilation on demand, with high ventilation when it's required and less when it's not. This leads to a cost-effective and safe way to decrease operator exposure to toxins. The system will also maintain a constant negative pressure inside the BCR when not in use, so any leaks or openings will draw air in rather than letting contaminants out. Along with a secondary containment enclosure, also kept under negative pressure, this will prevent hazardous materials from migrating outside of the BCR, ensuring the safety of everyone nearby. Figure Engineering has developed ACTAV as a modular system, where we can suggest solutions for any budget that offer the greatest return of investment. Furthermore, this allows for a phased implementation, utilizing funds as they become available, allowing you to make the greatest impact now and further improvements in the future. These solutions result in reduced operating costs and workman's comp claims. Instead of providing a sloppy quick fix, Figure Engineering will evaluate each BCR to determine the most cost-effective solution. This could be as simple as repairing or upgrading components of the existing BCR, with the addition of sensors and controllers, leaving most of the BCR unchanged. In addition, Figure Engineering has developed a process known as dust migration mapping to find the sources of hazardous material generation in and around a blast cleaning room. Implementation of the current ACTAV system does not mean that you'll have to completely replace your current blast cleaning room. Figure Engineering will evaluate existing systems to determine the contributing factors of poor ventilation and leakage to propose solutions for any given budget. The ACTAV system uses a collection of sensors to evaluate environmental conditions inside of the blast cleaning room. The heart of these sensors is the Continuous Hazardous Environmental Monitor, or CHEM sensor, which measures bulk dust in the airstream, and a real-time analysis of chromium and cadmium dust concentrations is used to correlate bulk dust levels to the personal exposure limit. Collected data is then evaluated by the control system, which in turn adjusts the ventilation to provide correct amounts of airflow for the detected environmental conditions. This process ensures that blast operators remain below the OSHA PEL while minimizing the energy required to maintain proper ventilation. This graph represents airflow and dust concentrations over the course of a typical blasting session. When we start, airflow is low as the system is in an idle state, just enough to maintain a negative pressure in the booth. The operators will first turn on the system and it will go from idle into a normal operational mode. They'll begin blasting. As you can see, dust will start to rise. Now it maintains in this safe operating area for a while until a second blaster begins blasting as well. We then cross over into the second threshold. the system will automatically trigger to go from normal operation into HAZBlast operation, increasing the airflow. As soon as this airflow is increased, dust concentrations will immediately decrease in response and remain in this safe working zone in the HAZBlast airflow mode until the second blaster stops blasting and we're back down to one blaster, at which point dust concentrations will also decrease. The system will recognize this and return from the HAZBlast mode back to a normal blasting mode to conserve energy and reduce operating costs. Once blasting is complete, operators initiate a purge mode, which puts the system into a maximum airflow state for a brief period of time, after which it will return to a low power idle state, maintaining constant negative pressure until the next blasting operation starts. To be more robust, the ACTAV system includes a keyed override switch, allowing the key holder to put the system into a manual operation mode. The BCR can then be manually set to provide the desired amount of airflow regardless of sensory input, essentially reverting the BCR to the current passive ventilation system. This allows the blasting operations to continue if the system needs servicing. However, continuous operation in this manual mode is not ideal, as high airflow settings will increase operational costs, while low airflow settings will increase exposure to airborne toxins. The brain of the ACTAV system is a programmable logic controller. This PLC can be easily reprogrammed or updated to account for changes to system requirements, more restrictive cadmium and chromium PELs, or PELs for new substances. Similarly, the chem sensor is capable of detecting additional toxins. To advance this prototype technology to a full commercial application that can be used in any blast cleaning room on any base, Engineering has been awarded a SBIR Phase 2 contract enhancement, as well as a Rapid Innovation Fund project to further develop and ruggedize this technology into a full-scale working prototype in the blast cleaning room located in Building 844 at Hill Air Force Base. Successful completion of these contracts will help to further commercialize the ACTAV system and bring it to a level where it can be quickly and affordably implemented into any current or newly manufactured BCR. In summation, Air Force personnel are exposed to dangerous levels of cadmium and chromium dust known to cause cancer. Figure Engineering has developed and demonstrated a solution in the ACTAV system, which keeps workers safe at a reduced operating cost.